Okay, we can start. I'll just minimize this. Good. So the plan for today is, of course, as usual, if you have questions and doubts that you want to discuss, there's time for that. Otherwise, I'll be zooming out very briefly to contextualize what we've been doing last week into the general idea of a Bayesian workshop and the two readings that you had to do or that were recommended for last week. Then I thought that we would still spend a bit more time do quality checks on the memory model because that brings up some issues that I want us to discuss before we move on to multi-level. And then we will start the multi-level modeling and that will spill over next week. Questions? All clear. Now you can just program anything instead. Okay. I haven't checked this morning the question and answer Google Doc, but as far as I could see yesterday or the day before when I checked, there weren't any other questions. But I'll check again. Okay, what is a good workflow? So if we look at the literature on industrial workshop workflows or software workflows, they're defined as a sequence of processes through which a piece of work, here a model or an analysis, passes from initiation to completion. And in the context of Bayesian workflows, this means creating a scaffolding of operations that ensure that your model and analysis can do what you think it can do or what you're telling it to do. What are its limits and caution to take when making an inference, et cetera, et cetera. In a sense, it's a good set of practices to actually stress test your model to figure out if it really works. And often, especially as you progress and develop your own models, it's a good way of thinking through your model and making sure that you're actually building it in a solid way. So in one of the two papers, the 10 rules for computational studies, this is how it looks like. And I'll just move this thing away because it's always in the way. Okay. And so basically, they're putting it in the context of experimental research. So it says design experiment, build models. Then you want to simulate, model, and experiment, which is more or less what we've been doing so far. You want to see whether you can recover the parameters. We've seen that. You want to see whether you can recover the model, and we'll see that at a later stage. If the model and experiment seem to work, right, you can actually discriminate between different models of matching pennies with the amount of trials that you're administering to your participants. Then you can move to the next stage. Otherwise, you go back, right? And you change. What if we have more trials? What if we have more participants? What if instead of having a random bias that our participants are playing against, we put alternating random biases or something else, right? Once things finally work, right, we fit to the real data, we see whether the model is fitting in meaningful ways, the parameter values, whether comparing models gives meaningful results, and then we check whether the model is actually predicting the data in a meaningful way and not in a super biased way. If that's not the case, we go back to start. Otherwise, yeah, so there's an analysis of the parameters that we've inferred and a report of the results. And this is kind of not, it feels a lot of work to do, but it's nice down to the bone Bayesian workflow. Because if you go to the other huge paper called Bayesian Workflow by Gelman et al., actually here we get a much more comprehensive perspective, where there's a lot of impact elements from the more skinny workflow that we saw before, right? So for instance, here you see that you pick the model or develop it, then you can do prior predictive checks and see whether the prior predictions actually fit with the domain expert knowledge. If not, you modify the model, right? Otherwise, you can fit the model, uh, and then blah, blah, blah. And I really like in this really huge workflow, this step, right? Which is give up. Because sometimes I had several cases where I really thought that, the really cool model incorporate these and that, and there's just no way to make it work with the data that I have. So it's much better to actually work with simpler model that are not doing all the things I wanted to do, but at least I know that they're giving reliable results. This paper is actually is being turned into a handbook, so it's really dense and there's lots of stuff. I'm not gonna go through all the details, but we focus on the steps that we've seen so far. So prior, posterior checks, prior, posterior updates. So how do we then go through a more complex model and again apply the same workflow that we've seen last week? I'm gonna take the memory model, right? And we've seen already that we want to pick a model for the example that has perfect memory. And we've seen last time there's a couple of other possibilities that are developed in the course notes. I'm not going to discuss now. And the perfect memory says that the memory at any given trial is given by the memory at the previous trial, updated by the predictive error, discounted by how far we are in the trial, right? So that if we're early in the trials, then the predictive error is changing our memory state a lot. Otherwise, it's changing it a little because this is a perfect memory model that doesn't forget the full past, right? So here we had our representation of the model as the random bias one. And what we want to say is that the theta is not just a parameter that needs to be inferred, but is given by at least two components. One is a bias, and the other is the memory, right? The memory modulated by a certain parameter because the model might remember everything perfectly, but might decide to give it a high weight or a low weight, right? To be swayed by memory or not. And so what we do is we say, well, we could say that memory is externally given, is observed, because we can observe the cumulative rate of picking right. So we put it as a dark gray arrow or a dark gray box going in with an arrow. And then we have two new parameters, the bias and the beta, which are what we want to estimate from the data, from the data. We specify on the right our equation, which theta, which is a rate, it goes between 0 and 1, is going to be the inverse logit of bias plus beta times memory. And we're going to have two parameters, the bias and the beta, that need priors. So we can have that, for instance, in logout space, bias is a normally distributed prior variable with a mean of 0 and a standard deviation of 1. And beta, it could be a smaller one, right? That goes between with a mean of 0 and a standard deviation of 0.3, right? Why? Well, we can run prior predictive checks, which we will do in a second. If we make beta too big, right? Both bias and beta as big as bias, then we're going to have all the probability in the very limits, right? We could have done something different and say actually bias is something that we don't care very much on. So we're going to put a narrower prior on that. And we're going to put a broader prior on beta because we're more interested in the memory effect, right? That's a theoretical choice. Questions so far? Right? We're just building the model. Should be quite straightforward. So then what we do is, and sorry, haven't had the time yet to turn all my stand code into white background. But what we have is we have a data chunk on the top. which has the usual suspects. It has a number of trials. It has the choices of the agent that we're trying to infer, and it has the choices of the antagonist or the opponent of the agent that we're trying to deal with, that we're trying to infer. We have two parameters, right? We just discussed the bias and the beta. And then what we have is a transform parameter in which we're trying to uh, create the memory state on a trial by trial basis, right? So we loop through the trials. If it's the first trial, we set memory to 0.5, no memory, basically. Everything is equally likely. And actually, somebody was making me notice last Tuesday that this could actually be put outside, so it doesn't check every time. It's slightly faster. I have a note to redo it. Then if the trial is less than n, meaning it's not the very last trial where updates doesn't make much sense, we have the exact same formula that we saw in the slide, in a couple of slides before, that the memory at trial plus 1 is equal to the memory at trial plus the predictive error divided trial plus 1, right? So shrunk according to how far we are in the trials. And then we have here a brutal hack that says, if by chance all the previous choices have been left so that the memory is 0, that would be very bad in logouts space. It would be minus infinite. So we push it a bit towards the center, and we say it should be 0.01. There's more elegant ways of doing this. I've put an example in the course notes where we do it in a Bayesian fashion, right? Where the agent is on a trial by trial basis inferring the rate of the other using Bayes. But the code gets a bit more complicated, so this is good for keeping it simple at this stage. We do the same if all of the previous trials were right. That means that the memory is 1. And we push it a bit towards the center and say 0.99. Then we need to write the model to be estimated. We have two priors, and I can see here I've actually switched. So bias is now 0 and zero point 0.3. I should update the previous slide. And then here we have that beta is 0 and zero point 0.5. Right. Then we have a model that, contrary to the previous model that could take all the trials into account at the same time, actually it needs to be run on a trial by trial base because memory gets updated. Right? So we have that for each trial, the likelihood is a Bernoulli logit log probability mass function in which the outcome is h at trial, right? Only that very specific value, which is determined by our formula, bias plus beta times the memory trial. There's a small adjustment that we need to do, which is if we're working on a logout scale, right, memory should also be on the same scale, so that if it's towards more likely to point to a left, it should be a negative value. And if it's more likely to be a right, it should be a positive value. So here there is a transformation that says take memory and turn it into logit space, logout space, right? Which keeps it consistent with the rest of the equation. That's all on logout scale. Why are we working on the logout scale? Well, because we want to ensure that our rate theta is between 0 and 1. And suddenly we have several components, right? Bias could in principle go between 0 and 1, right? We could have an agent that's just going left or an agent that just goes right. But then to that we add beta something, which means that it's even if we put boundaries on bias, it very easily goes beyond 1 and 0. We could have that we have an agent that we're trying to fit that is just going left all the time, and another agent that actually is swayed by memory. And so any sort of boundaries that we artificially put on bias or on beta will not describe equally well all the participants. So we put the boundary only at the very end. We allow bias and beta to vary as much as they want in this infinite space so that we can uh, allow the model to fit very diverse data. Right? And that requires us to do the slight mental gymnastic to actually turn memory into that very same space. Does this make sense? Okay, so we then create the model, and on top of that, what we do is we add some generated quantities, right? Because now we're starting to do uh, all our model quality checks. And so what we have is we have bias prior and beta prior, so we can save the priors for our prior predictive checks and for our prior posterior updates. The real number, they're in these infinite space of log odds. We then create prior predictions and posterior predictions. And now that we're working with simulated data, I did something slightly different than before. That is, before, this is not really good. Are there other colors somewhere? No, I'll just go and get them in the break. So I'll do it by voice. So what we did before is we took all the data that they were already there, let's say 120 trials, right? And we say, given the priors, what would we predict the model to expect in terms of how many of these 120 trials have one right, or two right, or three right, and then we draw the histogram. Here, we also have an additional memory state, right? And the memory state will impact the predictions of the model. So what we can do is to take three levels of memory, which are, meaningfully representing the possibilities of the model, and then run predictions for those values. Right? So here I have prior predictions when memory is 0.5, where we don't know anything, and the same for posterior predictions. Prior predictions for when the memory is 0.7, and the same for posterior predictions, and prior prediction for when the memory is 0.9. In this case, as it was exploding beyond the slide, I decided to only keep the asymmetry of one side, assuming that if we go below 0.5, we should see the same patterns but mirrored, right? It's usually a good idea to check because we never know which kind of weird stuff we might have done to our model, right? Then we generate the priors, right? We say, and I really, really need to go and redo these things because I've changed them throughout the years. And now suddenly the bias is 0 and 0.1. So I'll change that. We do a random number generator according to a normal distribution with a mean of 0 and a standard deviation that should be the same as the parameter above. Yes? Yes. So that's what we did in the we showed when we were doing the prior sensitivity code. Uh, the reason for which it's not implemented there is that I haven't had the time to fully update the slides, and this year I put the prior sensitivity checks before we went into this stuff. So when I prepared this slide, I hadn't yet introduced to that class, to last year's class, using the uh, variable that we give in the data, right? In that sense, that's perfect, right? That would be, sorry, this one. That would be the best way of going because it reduces errors. Good. Then we have the prior predictions. We have a random number generator following a binomial with an n of n, as many trials as we give through the data. So in that sense, that would be exactly the same operation. Then we have our equation, bias, which is just bias prior because we haven't fitted it to the data, plus beta prior times the memory level. And all of these goes through a inverse logit. So it goes from whatever space this is, log odds, into a 0 to 1 space. We do the same for the prediction with a memory that tends slightly towards the right and a memory that tends strongly towards the right. Yes? Mhm. Uh, the prior values, yes. So the bias is saying, I cannot really see it, but it's saying if we have no memory, what's the propensity to pick right or left? Right? We are centering it at 0, so it's most probable there's no propensity. And there we're putting a standard deviation of 0.1, which means roughly that it goes to 0.3 and to minus 0.3 as the kind of probabilities, right? We don't expect a lot of probability with a lot of probability that the bias is going to be beyond zero point 0.3. Now, these range minus zero point 0.3 and zero point 0.3 are completely meaningless, or not they're completely meaningless, but they're hard to intuit in what they actually means in log space. So if we assume that memory is neutral, what we can do is that we can say in logit, and I guess we can use the BRMS in logit scale, and then we can say what is minus 0.3 as, and I can't remember, but it's something very small. So we're assuming that the bias is very small. And then we do the same for 0.3, which is going to be mirror just on the other side. And so we could expect that the original bias that the prior sees is something in between, let's say, 0.4 and 0.6, right? We expect that at most the model, the agent that we're trying to infer, will tend towards left slightly, 10% more than towards right, or vice versa. And that if there is a bigger bias, the data really has to push for it, right? It really has to have a strong evidence for a bias. Does that make sense? You're perplexed. Alash. They should go in logit, yes. Mm-hmm. So I think it depends on what we're trying to do. So a good reason for picking these evenly spaced values in memory space is that it's simply saying, without really knowing anything else, what would the prior say when memory is neutral, when memory is slightly biased, and when memory is strongly biased, right? So it's just a very early sanity check. What then we would do once we start working with more complex data is we can actually take the memory state of the agents actually playing the game, right? And then we can do more complex visualizations where we say, well, actually bin and tell us where is the memory state, and then we can represent the expectations of the model, right? At this stage, it's simply to see, is the model working? Yes. Oh, it's a memory that most of that quite a few of the previous games ended up in the agent, the opponent picking right. That would be a 0.7. And a memory of a game in which the opponent mostly picked right, that would be 0.9. It's biased in the sense that it points in one direction compared to another. Yeah. So we're just saying if the evidence for the agent points right, strongly, in a medium way, or not at all, what would the model expect? So it's just a way of saying, for instance, given that beta is different from zero, would we see an effect of memory? Because if we don't see an effect of memory, the model is not working as we think. Then we do the same for the posterior predictions. And then we need to create some data in order to fit this model. Right here again, I rely on the previous big simulation. So I subset so that for simplicity, we just put a noise of 0 because I'm going to show you that the inferences of the model are biased anyway, are problematic anyway. So, but we don't want to, we actually can show that the problem is there even without noise. We pick a rate of 0.8, which is quite decided towards right, so that we can see whether the model is learning. We create the cumulative rate, so we have an external memory state. And we do the same trick of avoiding that if by chance there were two or three choices in the same direction at the beginning, we have a 0 or a 1. Then we create our memory agent, and in logout space, we give it a bias of 0. Right? So there should be no bias, no tendency to pick left or right that is not determined by memory. We have a beta of 0.1, meaning that the agent mostly follows the memory. And then we have the memory agent, which has 3 parameters, the bias, the beta, and the cumulative rate, and makes a choice, one trial at a time, according to our in logit scaled of bias plus beta times logit scale cumulative rate. Right? It's the same function as before, the same equation as before. And then we run a loop that says, given each single trial, calculate the choice of the agent. Then we take this data that we created and we make data for Stan. Again, a list where n is 120, the number of trials. H is D1 self. That's the choices that we just generated for the memory agent. And other is the D1 other that we had generated above in the large simulation. Yes. So what we're doing is we'll simulate a game, right? So we pick the opponent, which is the random bias agent, right? Then we get a memory agent to play against that opponent. Right? At this point, we have the sequence of 120 trials, what the two agents have done. And we need that because we want our memory agent model in Stan to try to fit the data and reconstruct the underlying parameter values, right? Bias 0 and beta zero 9. And we work on simulated data because there we know what's going on, right? And therefore we can control whether the model is doing what it says it does, right? Yeah. Sorry, I should have made it more clear. So we fit our model, which means we write the Stan code that we wrote before. We specify where we've written it up. We compile the model, and then we use the compiled model to fit to the data. Are there questions on these code? Right, this is exactly the same code we've seen last week. So there's data, there's a seed, there's how many chains we're running, how many parallel chains, and here it's two, it should be one because chains is one. So there's no way of splitting the same chain onto different cores. There's iter warm up, that's the number of iterations through which the model will learn the adapt delta, not the adapt delta, but the number of steps that it needs to take and how big these steps are as it explores the posterior space. Iter sampling, that is once we did the warm up and set these parameters, how many iterations we need to do. Refresh 0 if we don't want to see it running. Max tree depth and adapt delta, which are the hyperparameter where we're trying to tell the model to be really careful and learn a lot from every iteration in the warm-up and look a lot into the future to avoid always exploring the same area. Fits, it should fit in at most 1 second, and then we have a summary. And we can see, we can apply our model quality checks to see whether this is doing what we think it's doing. So we can look at the prior predictive checks. And so here we simulate for each of the posterior samples, for each of the 1,000 iterations, how many of the 120 trials will be ones, will be right. We can see that there's a rough peak at 60, right? That's in the middle. And that there is decay or decline of the probability of a high number of ones or a high number of zeros, right? And here, just for the fun of it, I put the real n. And of course, since the model hasn't seen the data yet, right? This is just the prior predictive checks. It hasn't really impacted the estimate. We can use that to say, well, the model at least can capture, although at a low expectation, the actual data, right? It's not going to completely discount it. Yes. Mm-hmm. No. But let's unpack that question. So you're saying now our model seems to be informative, our prior. So we have a bias which is very conservative. It's saying we don't expect a lot of bias. And we have a beta, which again is a bit broader, but it doesn't expect, memory determining everything, right? As soon as there is a slight evidence towards right, to just go right every time. If we try to give broader priors, right, wouldn't the model be better and learn more from the data? That's the question, right? So here I miss my color, but if you remember, right, if since we are in logout space, if we give a broader prior, let's say that both bias and beta are a normal distribution with a mean of 0 and a standard deviation of 1, what we have is that first already just the bias pushes the probability space to the very sides, right? Because it says that we can expect biases between -3 and +3 on logout space, which is between 0.02 something and 0.97 something, right? So this underlying theta, just as determined by bias, is going to be pretty broad. To that, we add bias, right? Which sort of pushes out the probability density, right? It says it can actually go much, much broader. But as it pushes it in a logout space below -3 and below +3, we're going to have in logout space something that still looks thin, but it goes very much out, right? For instance, -6 and +6 at the very least. Yes, something like that, depending on the memory value. But once we squeeze it back into probability space, all that long tail is going to pile up, transforming the probability density into a U shape, which means that the model actually is quite persuaded that the agent will either play all zeros or all ones. And in that sense, it becomes very informative in a way that we don't want, right? So that's where non-informative actually ends up being very informative. Um, These also has implications for computation because as we move towards the margin of logout space, -6 and -20 are really not that different in terms of log posterior probability, right? Because in probability space, they're very close. And so the Markov chain algorithm will spend a lot of time exploring that tail, saying, oh, things are changing slightly. Maybe I should go, right? And they're changing slightly here. Maybe you should go. And they're changing slightly here. Maybe you should go. And it can go indefinitely, right? -30, -40, -50. They don't really make a huge difference in terms of how likely it is to generate a certain set of data. And therefore, it can really spend a lot of time in that tail, trying out how these values would work. And so by constraining it a bit away from the tails, we are saving the computer a lot of time, saying, well, actually, the further you go, the more you should discount the probability, and therefore it should be harder to move in that direction and explore it, because mathematically it doesn't make a difference. The same is also, so a slightly difference when we talk about, let's say, effect sizes in a standardized space, which in principle you can have an effect size of 20, right? And an effect size of -20. And you could say, should we have a uniform distribution between -infinite and +infinite? And just let the data tell us what the difference is, right? Which approximates frequentist statistics. But that would sort of say, well, we're betraying what we know. So we know that we run experiments that are not run on the full population, right? So we are at risk of seeing a pattern in the data that is nothing but noise. And we have a bunch of previous studies, let's say we're working in psychology or cognitive science, that say that humans are so complicated that really there's no one factor that has a huge impact on everything, right? So we could expect that, any effect size above one is less likely. And again, if we use these priors, we are embodying some meaningful knowledge, right? And we're saving computation to the computer because it doesn't go and explore 7 or 8 if coins d, right? And then if the data is really pushing that way, once we do the prior and posterior update checks, we'll see that, right? And then we can discuss, oh, is this because actually there is a huge effect here? Or maybe it is because there's an issue in the data generation process, or we should replicate the experiment and make sure that we actually see these big effects, right? That are implausible given what we know about human cognitive systems. So it's a really good question, right? Why shouldn't we let the data speak? And the answer is because the data is noisy, right? So we want to integrate the data with some sanity check from what we actually know, right? We're not starting as a blank slate. We always know something. And this is not pushing in any specific direction. It's just saying, actually, we know that effect sizes tend to be small in our field. So we discount extreme values. We're not searching for a specific result. We just discount extreme values in both directions. And when we work in logout space, that actually makes even more sense because the the nonlinear transformation would change our expectation in weird and counterintuitive ways. Good. Here I created another representation of exactly the same. So I plot on the as dots the times, the trials in which the agent picks 0 or 1, and you can see that the bias of the random, I'm sorry, the bias of the memory, not the bias, the choices of the memory agent, given that it was playing against a biased agent, are mostly towards 1, right? It picks up on the bias. And then we see the the theta according to prior, right? So we sum the beta and the bias, and then we see that the theta is really just randomly moving around, but very close to zero point 0.5, which is another nice sanity check. That is, we're not introducing a skew in the expected choices in our agent, in our model trying to infer the agent. Then we can look at prior posterior updates, right? So we fit the model to the data, we plot the prior in red and the posterior in blue for bias. Then I also put a vertical black line that indicates the true value in the simulation. So take a second to look at it and think about what you see in it. What are you seeing? Yes? Yes? Yes. Exactly. So you're seeing that the posterior estimate for bias is ironically biased. It's not the only, and we should keep this in mind. We could already speculate why, but let's wait a slide and then it will become even more clear. Do you see anything else when we check the posterior and the prior against each other? Yes? Hmm. Yes. Hmm. Yeah. So you're saying the model seems to have learned something about bias. Given this is a simulation, we actually know it has learned something wrong, but it has learned something, and and it seems to be more confident after having learned. A thing that I would note though is that for a model that is relatively simple and that's seen 120 trials, the increase in confidence is very small. So the model hasn't learned much. Right? The spread, the variation, the standard deviation of the prior and the posterior is not very different. Again, there are no hard-coded rules, but for instance, Gelman has suggested that if your posterior is not as not 1/10 of the standard deviation of your prior, and something important rides on that parameter, you should be very skeptical of your model because it means that your model hasn't learned much. I put no specific value on the value of 10, but it's just to say that this is clearly not 10, right? This is very far from 10. We also see that the posterior is pushing, right? So here the probability on the right is going pretty quickly towards zero, and the posterior is trying to go that direction. So if we had used a broader prior, it would have clearly gone more that direction. And it would have been more biased, right? It would have assumed more that the memory agent would tend to play right no matter what memory says. And I know we're on break time, but we'll get 10 minutes in 2 minutes. So here I look at this and I say, well, let's look at the beta parameter. So what we have here is a prior and a posterior. What do you see here? Beta? Yes. Well, it's at least twice as high, right? So it is much more certain compared to the previous one. Yes. Yeah. Do you see any bias in the beta estimation? Yes. So the bias is opposite compared to the other, right? So the bias parameter get pushed towards right, the beta parameter gets pushed towards left. Has, well, you were saying it's much more confident. We could discuss whether it has learned enough, right? Has the parameter been regularized, been biased by the prior? Well, again, we see that it's getting towards the tails, right? So maybe a broader prior would have lessened the bias here. Why do you think that bias is overestimated and beta is underestimated? Let's say you rerun the model where you broaden this, and I've done it, and this bias remains, like this left skew remains. Why do you think those two parameters are not reconstructing the true underlying value? Think about the conditions in which we're simulating the memory agent. What is the memory agent playing against? Yes. Well, just against one very biased agent. Yeah. And if the agent is very biased, right, the memory agent can display this very same behavior if it has a very good memory and no bias, or if it has some bias and a lower memory, right? Beta on memory. So the very same patterns can be explained by the true parameter values, but also other combinations of values. And given that the model is never the simulated agent is never playing against somebody with the opposite bias, this model has a hard time discriminating these two things. And indeed, if we plot the estimated posterior samples of the bias and of the beta, they're very strongly negatively correlated, meaning that you can get the same posterior likelihood with a higher bias and a lower beta, or with a higher beta and a lower bias. And that's, for instance, where we start having a lot of trade-offs on how we want to optimize our model, right? If we put a much broader prior on bias, right, then these is going to be even more pronounced, right? It's going to be even more squeezed because the bias can be adjusted much more. Right? Uh, if we put a much broader prior on beta, right, then we get that the model will start skewing things in a different way because it will put all the probabilities at 0 and 1s. Right? And that's where we want to play with this model before we go on the real data, because we want really to understand the trade-offs that we're making. Right? And with that, we will take a break of 10 minutes. So we'll see each other at 1:18. Okay, we should start again. So, oh, I have actually forgotten to put it on the whiteboard. Okay. Yes. So then what we can look is the posterior predictive checks. Right here we can see if we just run predictions from the model that has seen the data, suddenly we see that the distributions of peaking 1 over 120 trials is much more centered on the actual data, and it's much more narrow than the prior predictions. And if we run the same plot as before, that looks at how the propensity to pick right changes over time, again, we see that there is a very rapid learning and then a bit of a wandering around, but still staying quite high in the propensity to pick right, which, given what we see here in the choices of the agent, the actual choices of the agent, is quite representative, right? So at this point, what we can see is that the model that we feed to the data is quite good at capturing the behavior of the agent, but it has some issues in reconstructing the latent mechanism, right? It's not too bad, but we know there's biases. And here I took the predictions at low memory and medium memory. Oh, yeah. Sorry, last week has been terrible, so I had really good ideas to rerun all the slides, but I redo all the code, but I haven't updated all the slides. Yes. Yeah. Yes. Hmm. Yeah. So in we are giving the model the self choice and auto choice, which combined give it also the information on whether it gets one or not, right? So in that sense, it is getting that information. What we could do is we could also plot in the same way as we plotted the panels on the right, the performance, right? So we could say, let's put high up feedback of one, so a win, and below a loss. Let's look, given the priors, how much we expect it to perform. And after having seen the data, how well do we expect it to perform? Right. Well, yes, because if you pick like the agent, then you win, right? So it has embodied that knowledge in the way we built the model, but it's not using the feedback per se to change anything. That would be the reinforcement learning. Yeah. Then what I did is I took the three different levels of memory and I said, does it matter whether it's a memory state of 0 or a memory state of zero point 0.5? Because I reran the code and I changed the values, but I didn't change the slide. So here we have a low memory where the memory value is zero point 0.2. Here we have a neutral memory where the memory value is zero point 0.5. And here we have a high memory where the value of memory is zero point 0.8, right? Not zero point 0.5, zero point 0.7, zero point 0.9. Sorry, I'll fix the slides and I'll upload them again. We see in red what the model think will happen in um, before having seen the data. And we see in blue what the model think will happen after we've seen the data. In the lower panel, we have exactly the same thing, but using varying plots because sometimes shifting perspectives, I see more things, but it's really the same thing, just shifted vertical and made symmetric as a mirror. So what are we seeing here? So we're seeing that the prior model is not swayed by low memory, by memory of mostly left, is not swayed by memory of mostly right, still mostly picking once, right? Not once. It's mostly picking at random at 0.5. It's the same for neutral memory, so equal number of left and right, but it's actually much more confident that it's going to be 0.5. Why do you think that is? And that's why these visualizations are really good to help us understand the model, right? Why is the model much more confident when memory is 0 in logout scale? Yes. Uh, no, this is actually a more technical question. So because here we're representing theta, and theta is determined by two components, bias and beta times memory. If memory is 0, beta becomes 0, And all the uncertainty of that parameter disappears because it's always zero. While when memory is non-zero in logout space, all the different possible values of beta push some on the left and some on the right the prediction of theta, right? Because beta is a distribution, and so it has a certain uncertainty. And what we see in the middle panel is that the uncertainty of the beta parameter gets annihilated, literally made zero by a memory state of zero. So the model is much more confident, right? Which is a bit counterintuitive, but it allows us to understand the model better. Then we look at the posterior. We see that the posterior, right, is following the memory, right? Which tells us that the model, once it has seen the data, it learns that beta is non-zero. And it's positive, if you want, right? It is really following the memory. Does that make sense? Good. That was it for the memory model. Very briefly, what if we wanted to code the reinforcement learning? Right, we have a reward and we have a choice. We have a value and we have a probability of choosing one. We have a learning rate and we have a tau. Right? This is how we could represent it. We can code it. Right? We have the data that has the trials, the array with the choice, the array with feedback, and an initial value. We could have also determined it inside, right? Whether the agent has an opinion about the value of picking right and left in the first trial. We have two parameters, the learning rate and the tau, which I'm calling log inverse temperature, so that I remember that first it's inverse temperature and not temperature, which I always forget. And second, I'm putting it in log because that allows me to have it always. What happens if I work in log space? Yes. It's not log odds. It's actually log space. Yes. Yeah, it's always positive, right? By definition, the inverse temperature, the tau in the model, can only be a positive value. And so by putting it in log, I'm sort of ensuring that that's the case. I have here a transform parameter that says that the inverse temperature is the exponential of the log inverse temperature. And then I have a model where I have a vector of values, which I'm defining a value for choice 0, a value for choice 1, a vector of rate, and a vector for predictive error. And then I can say that there's a prior on learning rate, which is a beta because learning rate is between 0 and 1. And I can put it just between 0 and 1 using a beta prior. The log inverse temperature is a normal distribution with a mean of 0 and a standard deviation of 1. The value at the beginning is the initial value, and then I loop through the trials and I say that the rate is equal to the softmax of the inverse temperature times the value, and the model is the choice that the agent took at that point, given the rate. And then given that the model has made a choice, we can calculate a predictive error and update the value. I'm not going to spend too much time on that, but I think I'll publish soon, hopefully next week, the full course notes on with reinforcement learning as well. Now, I'm teaching the code as pedagogical as I can, and I know it's complicated. There's some ways of rewriting the code that we work with in a in a bit faster way, but when the models become more complex, much faster way. And I want to give you some references here so you know that. There's a book chapter that you can very quickly skim. It's called Speeding Up Your STEM Code. Um, and there's a video lecture by Jonathan Templin, which actually has a series of courses that it records, like I'm recording, on Bayesian psychometric models and Bayesian factorial models and the like. But there's a lot of good tips on how to make your code less transparent but more performative in those uh, two resources. I also want to bring up a few additional notes on why we're running all these simulations. And as you can see, I had fun with the what's called the designer thing in PowerPoint. Uh, and the fact is that it's with these model, even at the level of complexity that we're working now, which is relatively low, there are lots of weird things that can happen. We've just seen the bias and the beta that sort of squeeze themselves, right? And then the priors might have additional impact on these parameter values, et cetera, et cetera. So we want to use simulation because in these simulations, we know how the universe works, right? We know exactly what's happening. And that allows us to understand what the models are doing. It allows us to, for instance, check the prior sensitivity of the model, how much changing the priors will change our inference. It allows us to see how well the model can recover parameters, right? We've seen parameter recovery procedures. And we can also use to run stuff like power analysis, or how Bayesians like to call them, precision analysis, which are not exactly the same thing, even if the code is almost the same. And one thing, though, that I should pre-warn is that we can do all those things, but often my temptation is to do all of them at once, and then the simulation spirals out of control. So we've seen internal validity. We can use simulations to say, can the model infer true parameter values? That is, if we decide parameter values, bias of 0.8, or in a Winstay-Lewis shift, we can attribute different parameter values and simulate data. Can the model tell us the true value? Right. And what we were doing before when we were doing parameter recovery, right, we did it a bit in a vacuum, right? So we said, okay, we have our simulation, we have 120 trials. Can it recover the parameters? And it was recovering the parameters decently, even in case of noise, but does not need to be the case. So we could actually, we have to play with the task structure. And that's where these kind of analyses are really crucial before you design an experiment, for instance. So for instance, having one trial per participant will make it much harder to infer rate than 1,000 trials. But how many are needed? And that's where we usually run power analysis. I think that usually people tend to say how many participants, but actually you can change the number of trials and your answer will change. And so the power analysis in our framework so far would be using it as a tool for what we call type 2 error control, right? If we were to repeat the experiment n times and the conditions were x, for instance, noise is 0.1 and rate is 0.8, and we set alpha, that is the maximum overlap of our posterior estimate with the null hypothesis, which in the frequentist parlance would be the p-value under which we consider a finding significant. In our case, we'd say, given that we have a posterior distribution, how many of the posterior samples are incompatible with our hypothesis? let's say we assume that our population group 2 has a higher memory beta than our population group 1. We can take the posterior samples of the beta of group 1 and group 2. We can subtract group 1 from group 2, right? In that distribution of the difference, because we can do the subtraction sample by sample, right? So we get a distribution of the difference. How many of the posterior samples are not above 0, are incompatible with our hypothesis that group 2 has a higher impact of memory than group 1. And then we can set that value to a certain acceptability. It shouldn't be above 5%. Then what we can say is if we only accept the simulations in which that number is not above 5%, right? We can calculate how many of these simulations gave us the correct answer. We would correctly reject the null hypothesis 5% of the time, right? Or 95% of the time, sorry. Yes, that's basically how a power analysis would work. Bayesians, since they don't like setting a threshold of saying 5% is super important, right? Or sometimes we're interested in different things, like we're interested in how well do we reconstruct the memory value, the beta value for our participants. So Bayesians like to talk about precisions. So we want to infer bias or beta, and we decide how certain the estimate should be. For instance, we should get the first decimal right. We have a precision boundary of 0.1. The error shouldn't be bigger than 0.1 on average. So in this case, we decide for a desired precision of the estimate of 0.05, because if we go 2 standard deviation from the mean, we're still within the 0.1. And then what we do is we say, we run our simulation, we fit our model, we calculate the standard deviation of the inferred posterior parameter for beta. And then we see, as we increase the number of trials, how many trials do we need to be reliably with a standard deviation that is below 0.05? And that's how a precision analysis works. The code is almost the same. The only thing is, how do we define the acceptability of a simulation? Does that make sense? So this was just to give you a rounder view of why we're doing all these simulations, because we can do a bunch of things, even old things that you were presented with. I think you did. Yeah, we did power/precision analysis in method 3, I think. Okay, now we can start working on multi-level modeling. So what is a multi-level model? A multi-level model is a model in which the parameters have a hierarchical structure. They have more than one layer. For instance, we have individual participants and the population group. Or, for instance, if we're doing a meta-analysis, we have individual studies and, let's say, the research group producing the individual studies and the meta-analytic estimates, right? Because each individual study might have a different effect, a result, and a research group, in the best possible word, has specific experimental and analytic procedures, so they might have results within a certain range. And the meta-analysis is trying to actually infer across all the research groups what's the effect size of these, intervention. Or we can have, right, in Actually, we could make it slightly more complicated. In a traditional experiment, right, we will have stimuli, 10 faces that are shown to all participants. And orthogonal to that, we have individuals. And on top of both of those, we have the effect size that we're interested in, right? So how do we introduce that hierarchical structure in our models? And again, we're going to start with the very simple random biased model. We have the choice, which is determined by a rate or theta, which is the simplest model we've seen. We know that this happens across a bunch of trials, right? But that can also be nested within a bunch of subjects, right? Each choice is determined by which trial we are at, but also which subject is making the choice, because different subjects will make different choices. Right? And trials is nested within subject because each subject goes through all the trials. Right? You can see here that the only variable that has subscripts is choice. Theta has no subscript. That means that these specific representation is inferring that all the subjects have the same theta, right? Meaning they have the same bias, which is not necessarily a bad idea, but it's most likely a bad idea, right? Especially if we're interested in using these models to understand something about group variations or individual variations. So what if we take theta and now we work purely conceptually? We just add a subscript there, right? Theta is not captured by the trials, right? And is dependent on the nature of the subject, on the idea of the subject. Right? So now what we're doing is we're saying that each subject can have a completely different bias from any other subject, right? Which is probably a step forward, right? Are we missing something? Yes. Uh, Yes, I think that yes, we are missing the priors, but I'm thinking before we go into the priors, right, in this space of possibility, right? Here is seen one subject, you've seen them all. On the right, it's seen one subject, you've seen one subject, right? Do we need to be so extreme, right? Is there a middle ground between these two opposite positions? Yes. Yes. So we can say that these subjects are not completely independent from each other, but they are part of the same population level, right? So that seeing one subject, you've learned something about all the other subjects, but not everything, right? And so instead of just having the thetas that are completely independent from each other and have their own prior, let's say a normal of 0 and 1, uh, we can say that there is an underlying mean to all of the participants and an underlying standard deviation, which is average variation of the participant from the population. Right? So by doing this, now we have parameters that are outside the single subject and therefore can regularize the inference of the single subject. Meaning, can as we're learning from the subjects, we can use all the other subjects to adjust the inference on the single one. And do this for all the subjects at the same time. So our choice at time t for subject 1 is determined through a Bernoulli by the underlying bias of each participant. The underlying bias of each participant has a prior distribution, which is a normal distribution with theta mean and theta standard deviation, which are the population level parameters. And the theta mean and the theta standard deviation have their own priors. So in a sense, the multi-level conceptualization is really at home in the Bayesian world because it's saying the prior for the individuals is the shared population level. These are three different pooling strategies that we've seen. We have the full pooling, meaning you want to use all the data from all the participants to determine the theta. And no pooling, that is, you only want to stick within each participant separately to estimate their theta. And the multi-level strategy, which is the partial pooling, where you keep separated individual theta, but they have shared priors, shared hyperparameters, a shared population level of parameters. Okay, so we have a whole 13 minutes, so we can actually look at what happens when we have more than one parameter. Here we have the memory model. We have the choice for participant I at times t, and the choice of the opponent for participant I at times t. Right? The other choice impact memory. Memory impacts theta. Bias and beta impact theta. Theta is determining the choice on a trial by trial base, individual by individual base. So it has the subscript I and T. Memory is also something that changes differently by participant by trial. But bias and beta are two parameters which are unique for the individual across all the trials. And if we want to make explicit that they're not independent subject by subject, it's not a no pooling, but it is a partial pooling. We show that there are shared population level parameters that determine the individual. This is just for the fun of it, how the win-stay lose shift looks like in this representation. Again, we have choice and other choice, which determine the feedback, which now is taken clearly into account because it's win, lose, and then a choice, not a memory of what the other is doing. The feedback affects the theta together with the lose beta, win beta, and bias if we keep bias. Bias, win beta, and lose beta are at the individual level. Each individual has its own parameter. But each of them have population level parameters. Does this make sense? Right. We'll get to the code, right? Now we really want to have the sort of conceptual part in place. Here again, we have the reinforcement learning, which has within the trial level, the choice, other choice, feedback value, theta. Within the subject level, the tau, inverse temperature, and alpha, learning rate. And outside, the population level parameters, right? Which are shared across all the participants, right? We might have in principle two groups, right? Then we would need to put an additional frame around and say group. And then in most cases, we don't assume that the two groups have shared hyper parameters, right? Because we're interested in the difference. Okay, So what if we want to get coding with these models? We're going to be simulating the random bias agent and memory agent. And let's give me a second. Yes. Okay. So what we want to do is we want to generate a choice of 0 and 1 where each agent, agent 1, has a specific distribution. And agent 2 and 3 have each their own specific distributions. And we want to generate those specific distribution from a common underlying distribution, which is just another way of representing what I was representing before. So we start and say, how many agents do we have? And here I'm putting 100. We're going to say, how many trials do we have? And here I'm putting 120. How much noise is there in the measurement? And here I'm just going to put 0.2 for the fun of it, because now we have a super powerful model, the multi-level model. Let's see if it can deal with that. Then we have bias agent parameters, which now we're going to be working on logout scale. So we're going to say that the rate, the mean rate across the agents, so of the population of random agents, is going to be 1.386, which is zero 0.8 once you put it back into probability space. The standard deviation is 0.65. How do I determine that? Well, I wanted a variability in the underlying rate of about 0.1. So I went to my R studio and tried out different values until I got approximately that in the probability space. Then we have agent memory parameters. And just because I still haven't updated the slide, instead of bias, it's called alpha. But we have a bias across the population that is 0, with a standard deviation across the population that is 0.1, meaning that most agents will not have a strong bias. They will be very close around 0. We have a beta of 1.5, which means that it goes above face value in evaluating memory, meaning that if the memory is slightly towards the right, it will more than that peak right. And then we have a beta standard deviation, which is 0.3, which again, when transformed back into probability space, gave us something meaningful that would be around 0.1. Then I simulated saying for each agent in 1 to 100, 1 to the number of agents, generate a rate from the normal distribution with a mean of rate mean and a standard deviation of rate. Generate a bias for the memory agent from the bias mean and the bias standard deviation. Generate a beta for the memory agent from the beta mean and the beta standard deviation. Initialize 3 vectors with NAs, with 1 NA per each trial. We call the first vector the choice for the random agent. We call the second vector the choice for the memory agent. And we call the third vector the memory rate, what the memory is being updated in that individual, in that agent. Then we have that agent goes through the 100 something trials. Go. And we have that the random choice of the random agent is going to be generated according to the random agent function with the rate parameter and the noise parameter. If the trial is the first trial, the memory agent will generate it according to a purely random process. If it's not the first trial, then the memory agent will make a choice according to its bias parameter, its beta parameter, and its memory. Then we create a temporary table or data frame where we collect the number of the agent, which trial we are in, the random choice, the rate for the random, the parameter that we use to the biased agent, the memory choice, the updating memory rate, the noise parameter, the mean rate parameter, the SD rate parameter, etc. Right? All the parameters so we can keep them in mind and we can make visualizations after. Right? Then if it's the first agent, we just create this is our data frame. If it's the agent above one, then we just attach the uh, data that we just generated to the previously generated data. Then we create our old cumulative sum function for both the random and the memory, so we can see how their propensity to pick right and left changes over time. And then we can plot. And we can see on the left the propensity of the random agent to pick left in a cumulative fashion, right? So at the beginning, it's very all over the place because even if the rate is skewed towards right, they can still pick zero. But as they play more and more trials, the average of their choices starts stabilizing towards their actual rate. And we can see that their actual rate, as we can observe from their behavior, is quite widespread, right? It's supposed to be, I can't remember how much it was, 0.8, yes, here. But since we gave it some noise and we gave some standard deviation, it spread all the way from 0.5 to 0.9, and there's an agent that got by chance a rate that was actually much lower. Then we look at what the memory agents are doing, and they're kind of picking up on the same regional values, right? I want to do some sanity check. That's probably the last thing that we'll do for today. And so what I want to know is whether the memory agents are actually learning from the agent they're playing against. So what I do is I plot on the x-axis the rate for the random agent, and on the y-axis the rate for the memory agent that's playing against it. I do that after 10 trials. We can see that the red line would be having learned perfectly what the other agent is doing. We're not there, but the blue slope, which is the actual correlation between the two, is very strongly positive. And there is some spread, but well, it's only 10 trials. We go at 60 trials, and it starts being more and more squeezed around the diagonal. And we can see that the blue and the red lines are much more aligned. And we go to 120 trials, and it has squeezed a bit, right? But it's not completely there. What do you think that is? There's noise, right? Both the memory agent and the random bias agent are behaving with a 20% noise. So no matter how many trials you will have, the correlation per se is going to be pretty much on par, but the single rates are going to deviate from the diagonal, right? If we didn't see that, we should worry because we explicitly put noise in the model. And so what we're going to do Next week is we're going to be building the stand code that from these data that we simulated can reconstruct the parameter values. So thank you.